So thanks for inviting me to talk about this. It's kind of a subject that's close to my heart, and it's about the minimum circuit size problem, or MCSP. And I guess if you were here a few minutes ago, then I kind of went through the spiel about what the outline is. But just to say a little bit again, first I'll start off with some background. And to me, this is kind of like maybe the most important part of the talk, in that I figure that a few months from now, maybe you won't remember the results or the techniques, but you can remember something about what MCSP is and why it's interesting. And then I'll talk about two results I proved last year related to MCSP, and finally I'll end with some application that isn't totally about MCSP. So if I lose you at this some place in here, or maybe you think that MCSP is not so interesting, you can kind of rejoin us over here. Okay. Oh, and I should say, so like when I practiced this talk, it took around 45 minutes. So there is like plenty of time to ask questions. Like feel free to interrupt me as you wish. Okay, so let's start with some background. And how I want to start here is I kind of want to tell you a little bit about what the motivation behind understanding MCSP is, like what maybe our results are kind of like a small piece of a larger program. And that's kind of like looking for fundamental problems in complexity theory. And what do I mean by that? So I want to like take a step back and like think about like what problems have we learned the most from in complexity theory. And I think probably after like a little bit of thought, you'll agree with me that SAT is like a really good answer to this. And in particular, by studying SAT, we learned about all these interesting different phenomena. We learned about NP completeness, PCPs, practically useful SAT solvers, theory of fine-grained complexity. And what I think makes SAT an interesting problem from the perspective of complexity theory, and what made it really fundamental, is that natural questions about the complexity of SAT, in particular, like, is it hard in the worst case? Can you approximate it? How hard is it on practical instances? What kind of algorithms can you use to solve it? They led to important unexpected advances in the field. So to me, that's what makes like SAT an interesting problem to study. And kind of a natural question you can ask is like, can we find other interesting problems that have this property, that like natural questions about its complexity might reveal further insight in the field to us? And so, SAT's a pretty fundamental problem. It would be like really, really amazing if we even found a problem that's kind of like half as fundamental as SAT. So the following statement's kind of really bold. MCSP, which is the minimum circuit size problem, and that I'll define on the next slide, is more fundamental than SAT. And this is kind of a crazy statement to make, because like everyone knows what SAT is, and I don't know how many people actually even know what MCSP is. So like this is like a really bold statement, and it's not at all proven yet. Like there's not good evidence for this yet. So what daring researcher would like dare make such a blasphemous claim? So my name is Rahul, but this is not me, Rahul. This is another Rahul Santanam. And so at this point, you're probably wondering, like, why are all these Rahuls interested in MCSP? Like, what's going on here? Why are they making these ridiculous claims? So to me, what makes MCSP interesting is the connections the problem has. It has connections to cryptography and learning theory. And to me, these connections really stand out because they're areas that maybe SAT doesn't connect so well to, like the connections between SAT and cryptography and learning aren't as tight as like maybe we would hope them to be. And it also has connections to aspects in structural complexity, average case complexity, and circuit complexity, maybe as you expect once I define it. So it has all these different connections, and moreover, we know like very little about the problem itself. Its complexity is a real mystery. Is it NP complete? We don't know. Is it hard to approximate? We don't know. Is there any algorithm that you can do to solve MCSP better than brute force? We don't know. But what we do know, kind of interestingly, is that answers to each of these three questions have significant implications on structural complexity, average case complexity, and circuit complexity. So in particular, we have theorems of the following form. If something is true about MCSP, what that implies kind of a solution to a long-standing open problem in kind of each of these fields. So in particular, if you can show MCSP is NP-complete under the usual type of many-one polynomial time reductions, that actually implies a breakthrough complexity class separation. It's something we believe, but no one knows how to prove. If it turns out that some certain approximation to MCSP is NP-complete, then there's this amazing breakthrough paper of Hirahara, which gives a worst case to average case reduction for all of NP. So like one of the classic criticisms of complexity theory is that it usually deals with the worst case, and we don't really have like a great understanding about what happens in certain average case settings. And what this theorem shows is that if you can show an approximation to MCSP is NP-complete, then a worst case complexity of NP and the average case complexity of NP for some definition of average is actually equivalent. And finally, if you could show that there are not like super efficient algorithms for solving some version of MCSP, which I won't tell you what it is, then by a hardness magnification theorem of McKay, Murray, and Williams, you get that NP doesn't have polynomial size circuits. So just to summarize what's on the slide, I guess the point that I want to get across is what's kind of interesting about MCSP is it seems to have these facets that like basic questions about the problem seem related to interesting conclusions throughout computer science. So maybe I'll pause here and I know I haven't even defined MCSP. I'll define MCSP on the next slide. But if there's any questions about maybe these connections or yeah, or maybe you are annoyed with me for making this claim, yeah. Okay. Okay, cool. So now let me define what MCSP is. So MCSP stands for the minimum circuit size problem, and it's defined as follows. So it takes two different inputs. The first is a truth table of a Boolean function. So you have some function f, and I just literally want to write down what all the values of the functions is on all of its inputs. And let's say lexicographic order. So this is some string, and I want to emphasize this is like a really long string. So if f takes like little n bits as input, this truth table is going to be of length 2 to the n. So it's a really long input there. And the second thing is it's going to take some size threshold. S, this is some integer. You can encode it in unary. That makes the problem like a little bit nicer, but it doesn't really matter. And the output is going to be, does there exist a circuit with at most S wires computing F? And to be really precise, I need to tell you exactly like what model of circuits we're considering. For now, I'll come back to this point later, but for now you can think of the usual and or not fan-in 2 circuits. Yeah, so are there any questions about the definition of MCSP?
So it's S wires, it's not the size, it's not the depth of the circuit.
Right, so you could imagine different size notions here. So like one thing might be wires, another thing might be gates. If you're over formulas, you might consider leaves. And later on in the talk, we'll actually use leaves as a size parameter, but you could imagine different versions of MCSP with different notions of size. So like depth would also be like a reasonable notion for what you'd want here. And yeah.
Okay.
Well, one kind of annoying thing is that like we don't really understand yet how like robust this definition is to things like changing it from number of wires to number of gates, or yeah. But I'll kind of come back to that maybe a little bit later. Okay, great. So just to give you some more intuition about this definition, maybe I'll give you a couple different interpretations of what this problem is. So perhaps the most natural way to interpret this problem is like as a circuit synthesis problem. So like maybe you're Intel and you need to design a circuit that computes addition on 16-bit numbers. You'd care about some version of the minimum circuit size problem because maybe you want to build the smallest circuit that does that. So it's a very natural circuit synthesis task. Another way you can think of this problem is kind of as like a compression task, where it's like you're given some string, some really long string, and you want to come up with kind of like a small representation for that string. And this representation will have kind of the nice property that if you want to know the ith bit of the string, you can compute that relatively quickly. And then finally, like some kind of cute interpretation I like to sometimes give people is that this problem is kind of about, or at least approximation versions of this problem is kind of about like distinguishing the strings which have kind of a high degree of computational order from things that are kind of chaotic. They're like don't really have a lot of structure. But yeah, so if you like that interpretation, you can take it. And so that's MCSP. Now let me just note some.
Can I ask a question at this point?
Yeah, sure, go for
it. Is there a search to decision reduction here, in the sense that you've stated the problem as a decision problem? Like, can you actually solve the circuit synthesis problem if you can solve the decision problem?
Yeah, so that's actually an excellent question. So we don't know if there is a search to decision reduction for this problem.
But that means that the interpretation of this problem as circuit synthesis is sort of a leap then.
Yeah, you could say that. Yeah, so we don't know there's a search to decision reduction for this problem, although, I would guess that there would be, because I'll come to it later, but it's kind of a big open question related to this problem, like, is there a search to decision reduction? Yeah, and one result actually from last year that I'm not going to talk about in this talk is that I proved kind of like a non-trivial search to decision reduction related to this problem. So where I showed like you can't get a polynomial time search to decision reduction, but you can get like a better than brute force search to decision reduction. But it's been a long-standing open question to give a search to decision reduction for this problem.
Thanks.
Yeah, okay. So some basic facts about the complexity of MCSP is one, it shouldn't be too hard to see that this problem is in NP. So you can, if you want to witness a yes instance, I could hand over a circuit of size at most S. And because this truth table is, really long, and maybe I give you the size threshold and unary, you can actually like go in and check, on every input, does that circuit evaluate to the right answer? So the problem is an NP, and that's not too hard to see. What might not be as easy to see is that this problem actually needs to be difficult if cryptography as we know it exists. So I don't want to get like too far into like how this is proved, but kind of the intuition behind it is that if cryptography exists, you can come up with pseudo-random strings that are kind of difficult to differentiate from random strings. But in terms of compressibility, these pseudo-random strings are kind of like highly compressible. Like I can, if I just know the seed, the pseudo-random generator evaluated that outputs that string, then I can like compress a pseudo-random string by a lot. So if you think of MCSP as kind of like a compression problem, it's sensible that it might be kind of hard for crypto.
So I was gonna, sorry, if I could ask a question or make a point, maybe I'm not sure, connection. I think in the early days of pack learning, this sounds exactly like the characteristics of pack learning. Like if one-way functions existed, you couldn't come up with a Boolean formula. You couldn't learn certain classes of Boolean formula at the time. So is that essentially kind of what you're saying right now? A pretty similar kind of result to that?
Yeah, it's a little bit more delicate than, I guess like the ideas behind proving it are a little bit more delicate in that in pack learning, you're not quite given the whole truth table. You're given like polynomially many samples. So there you don't quite need the crypto you need to come up with to make sure that like you can't Okay, let me not get lost in the weeds. It's a similar idea. And in fact, it's a good intuition for you to have, because it turns out, and I won't mention this so much in the talk, but it turns out algorithms for MCSP are in some sense equivalent to pack learning under the uniform distribution using membership queries. Yeah.
Okay, cool.
Yeah.
Thanks. I'll wait for that. Thanks.
Okay, great. So MCSP is an NP. It's probably not in P. A very natural question you can ask then is like, is MCSP NP complete? You know, and this is kind of going to be like the subject of the results that I'll talk about in this talk, which is going to be like 2 versions of showing MCSP is NP complete, not quite for MCSP, but for things that look like MCSP. Okay, so that's the problem. If there's any more questions, anyone wants to ask about the definition, they can ask it here. Okay, great. And now I just want to come back to a little bit more about what I think is interesting about MCSP. And I think I just want to mention like a line of research around MCSP right now that is very exciting. I mentioned that it has these connections to cryptography and to learning theory, but I didn't really talk about them so much. So I want to tell you maybe one of the connections that's involved with cryptography. In particular, there's a very exciting line of research going on right now, which is like trying to prove something along the lines of the following, which is that if MCSP is hard in the worst case, that's equivalent to MCSP being hard on average. And is MCSP being hard on average equivalent to one-way functions existing? So I already kind of like mentioned on the last slide that we already know like a reverse arrow from one-way functions exist, MCSP is hard in the worst case. And the hope here is that like, you can take this, you can kind of interpret that result as like MCSP being hard for cryptography. And this line of work is like hoping to show that maybe MCSP is kind of complete for cryptography. And so this would be like a really exciting line of work because it would kind of put the foundations of one-way functions on like a more solid complexity theoretic ground right now in terms of characterizing one-way functions. Like in the complexity theoretic landscape, they don't really fit so nicely. We don't really have a good characterization of them. And so this line of work is hoping to do that. And what's kind of exciting is there's actually been some significant progress in the past few years on this line of work. So I already mentioned this result of Hirahara, which like had this breakthrough result, which gave some sort of a worst case to average case reduction for approximating MCSP. And then last year at Fox, or I guess maybe, last year at Fox, Liu and Pass showed for some problem related to MCSP, which kind of trades circuits for Turing machines, you can actually prove that if that's hard on average, then one-way functions exist. And kind of like the main technical barrier to pushing all these equivalences through is that this Hirahara's result over here only works with one-sided error, and Liu and Pass's result over here kind of only works with basically one-sided error, and these one-sided errors are kind of in the wrong direction to compose them. But yeah, so I think this is like a very exciting line of work. It's not clear what major barriers it runs into at this point, and so I think it's a kind of exciting thing to look for over the next few years. All right, any questions about this? Okay, cool. And so now what that really motivates is like, so if it turns out that MCSP, its worst case complexity does characterize one-way functions, it's very natural to ask, is this problem NP hard? And so one thing that I didn't mention earlier that I guess I probably should have mentioned, if MCSP is NP hard, then it must have a search to decision reduction. This is related to Ronald's question. So you can think of the task of, so it's kind of weird that we don't have a search to decision reduction for it yet. So maybe you might interpret that as evidence it's not NP hard, but yeah, I just wanted to make that comment. Okay, so is MCSP NP hard? It turns out that this is like a very old open question in some sense. Turns out that people were studying MCSP in the 50s in the Soviet Union. They were kind of interested in this problem. And in fact, it was like such a like prominent problem in the Soviet Union that when Levin proved his version of the Cook-Levin theorem, he kind of has this quote. He didn't find the theory of NP completeness at first to be so interesting. So he said, like, I thought only extending the theory of NP completeness to some popular problems like graph isomorphism, circuit minimization, and or factoring would be worth publishing. I tried for a long time. So it's kind of funny looking at this today because like now we know graph isomorphism is like in quasi-polynomial time. We know that like factoring can't be NP hard unless the polynomial hierarchy collapses, but like circuit minimization, it's not clear yet whether it should be NP hard or not. And so what this means is like this has kind of been like an open question since the birth of NP completeness. And so this quote actually comes from a blog post by Levin that I had not seen before. And is kind of, if you're interested later, I can send you the link. He talks about how, in part, he discovered the theory of NP completeness because his roommate challenged him about the applications of theory. So that's kind of cute. So why is this, such a hard question to answer? Why is it so difficult? We know like thousands of problems are NP hard. Why is this one kind of difficult? And the reason is like when you look at what the difficult no instances of MCSP really are, what they correspond to functions requiring large circuits. And the difficulty with that is we don't really know functions requiring large circuits. Like we don't know how to come up with them. And what that means is that in some sense that you can make formal, coming up with a deterministic polynomial time reduction requires a breakthrough. And so like, what does this mean? Does it mean that like maybe we're not ready to attack the complexity of MCSP yet? Maybe we should like come back to it when we understand circuits better. I actually don't think so. I think there are kind of like two holes in here that we could hope to go through, and these holes are going to come up with my results when I talk about them later. One is like, what about randomized reductions? So like, it might be hard to come up with a difficult function deterministically, but if you're allowed to use randomness, all of a sudden it becomes very easy to come up with hard functions. Just pick a random function, that's going to be hard. So maybe randomized reduction is going to be helpful. Another thing is like, what about, instead of polynomial time reductions, what if I allowed you to use sub-exponential time reductions? Then all of a sudden you don't need to come up with functions requiring really large circuits, but you could get away theoretically with functions requiring like linear size circuits. And so both of these things are gonna, so I actually believe that you should be able to prove that ETH implies MCSP is not NP. And I think that like, I think it's definitely true, but I also think that like we might not be too far away from this. I don't think the techniques needed to prove this would have to be like crazy or anything. But yeah, so these are kind of two ways to prove hardness for MCSP that's going to come up later. And kind of the last bit of context I want to give you before I talk about our results, because it's kind of related to our results, is one of the reasons I think MCSP is interesting is, I think in some sense, proving hardness for MCSP is related to showing like kind of new types of circuit lower bounds. In particular, there's kind of this observation people have had that if you look at the techniques we have for proving circuit lower bounds, they all kind of prove circuit lower bounds that are easy to recognize. What do I mean by that? It means that like, if you look at the truth table of the function that it proves a hardness result for, it's kind of very easy to see, oh, okay, yeah, that actually is a hard function. So as an example, like if you look at the random restrictions approach to proving lower bounds against AC0, basically what that lower bound can say is like, if you look at this function, see if it simplifies under random, or does it ever evaluate to a constant under random restrictions? And if so, and if it doesn't, it's a hard function. So it's kind of like in polynomial time, given the truth table, you can check that it's a hard function. And this is very closely related to the natural proofs barrier of Razborov and Rudich. And what I think is interesting about MCSP is like, if you look at the instances of MCSP and kind of break them up into 4 different categories, like the difficult no instances, the easy no instances, the easy yes instances, and the difficult no yes instances. And so here by easy and difficult, I'm not going to make this formal, although you can, where I mean, like, there are some instances of MCSP that are kind of like easy to tell must be true or false, like kind of in a similar way that like there are instances of SAT that are kind of easy to tell or yes and no. And what this observation is kind of saying is that all the lower bounds we know kind of are no easy no instances of MCSP. And what then? Why that's important for reductions to MCSP is that, like, if you're giving a reduction from, say, SAT to MCSP, kind of the important instances that you care about are the difficult no instances and the difficult yes instances. Because if you gave a reduction from SAT to MCSP that only mapped into the easy instances, then your reduction, you've actually given more than a reduction, you've given an algorithm, because you can like first run the reduction to MCSP, you've only mapped it to easy instances, and then you can run an algorithm that solves those easy instances. And so I think one takeaway or one kind of conceptual result that came up in this work is that this kind of suggests that proving hardness for MCSP actually requires lower bounds of a different flavor than usual. Like maybe they don't have to be like better lower bounds in some sense or like anything like that. They just probably don't fit into the mold of lower bounds we already know. And that's kind of an abstract concept. This application that I'm going to talk about at the end is going to kind of be an example of this. I'm going to try and exemplify exemplify kind of a lower bound that comes up from our results that is of a different flavor than usual. Okay, so that ends like my background on MCSP. So I guess that was a significant portion of the talk. If there's any more questions about the background of MCSP, I know I didn't get to talk about like its connections to learning theory. If you like, I can maybe say a little bit more about that. But yeah. Okay. Cool. So that brings me to the results. So the results I'm going to talk about are from a Fox paper in 2020. And let me just give you, to start with, kind of an overview of what's going on. So I'm going to talk about hardness for two different versions of MCSP. For now, it's not so important what these two versions are. I'll define them later. And I do want to point out that last year we also did prove NP hardness for some other versions of MCSP, but I guess Bruno came and talked about this, I suppose. So I don't want to talk so much about that. But I'll talk about two hardness results for MCSP. And if you're not already maybe so familiar with MCSP, it's going to be like kind of difficult to interpret these results. So what I'm going to emphasize more of is what the takeaways from this result are. In particular, I want to the takeaways are going to be related to themes that I brought up in the background. So like, hopefully these versions are going to seem similar enough to MCSP that you think it suggests hardness for the original problem. It's going to be an example of how you can use randomness for showing MCSP is hard. We'll see kind of an example of these different looking circuit lower bounds, and we'll see a proof of concept of using ETH. But I'll be more concrete about that when we get there. Okay, so that's how this is going to go. So the first version that I'm going to talk about is a constant depth formula version of MCSP. So here, the inputs is the same as the regular version of MCSP. So you get a truth table of Boolean function and a size threshold. But now the output is going to be, does there exist a depth D formula with at most S leaves for computing F? So this is, kind of very natural. You can think about MCSP for different circuit classes, and this particular circuit class that we're considering is constant depth formulas. So prior to our work, NP hardness was known for the DNF version of MCSP. And in fact, this was proved all the way back in the late 70s, and there was like a bunch of different improvements to this work that tried to prove better hardness of approximations. One thing that I kind of want to point out here is that's kind of maybe perplexing at first is that it seems that like DNF MCSP should be an easier problem than the regular MCSP, right? Like, so DNFs are kind of a simpler model of computation. Conceivably, you could, it might be easier to find small circuits for DNFs than it would be for general circuits. And I would agree with this intuition, but no one knows how to make it formal. It seems difficult to be able to make it formal. So way back in the late 70s, we knew hardness for the DNF version of MCSP, and like people spent a lot of time optimizing that result. But it actually like took a long time before anybody even got beyond DNF. So like in 2018, Hirohara, Oliveira, and Santanam showed that like you can extend this result kind of slightly, but we didn't really get that far beyond DNFs. And this is maybe kind of strange when you like first encounter this, because it feels like we understand things like constant depth formulas and constant depth circuits pretty well. When we have exponential looking lower bounds for them, why is it that like it's so hard to prove hardness of MCSP for like even these circuit classes we think we understand pretty well? My personal explanation is that is kind of related to this connection with natural proofs. I think actually proving hardness for these problems requires maybe lower bounds of a different flavor than the usual ones. Okay, so now our theorem is we can prove that like for all constant d, that the depth d formula problem is NP-hard. And we do it using randomized quasi-polynomial time Turing reductions. So we, so I think the important parts to keep in mind about this theorem is that we're able to extend this for all depths d, and that it is a randomized reduction. And so now let me just mention I'm going to come back to what the ideas behind this are when I talk about the application. But kind of the main ideas are that we work by induction on the depth d. So these results here actually form our base case, the DNF problem. I think the approach is very natural. And the main technical thing that we accomplish is that we come up with a way to, in some sense, like lift lower bounds from the depth d problem to the depth d+1 problem. And I'll talk a little bit more about how we do this later in the talk. But those are kind of the two key ideas for that. All right, I think that's the last thing on this slide. Oh, okay, yeah. And so one nice takeaway from this is that it gives kind of like a really strong example of how randomness can be useful. So prior to this, there were some results that used randomness to prove hardness for MCSP, but this result is kind of interesting in that it uses randomness in like a very non-trivial way. Like previously, randomness was used to sample uniformly random functions. Here, randomness is not quite used to do uniformly random functions, but like something a little bit more subtle. So it's kind of interesting proof of concept. Okay, are there any questions about this result?
Can I ask a question?
Yeah.
This idea of a quasi-polynomial time Turing reduction is just about the time the reduction takes, or do you also allow the final instance of MCSP to be blown up quasi-polynomially compared to the instance you start with?
Yeah, that's a good question. So there is a little bit of a size blow up there.
More super polynomial.
Yeah, it's a super polynomial
Okay.
as well. So kind of the people were expecting that this reduction, if such a reduction existed, we could prove it, we'd probably only prove a quasi-polynomial time reduction, because we only know lower bounds against constant depth formulas that are like 2 to the n to the 1 over d. So you kind of expect, like, if you were going to try and convert such a lower bound into like a hardness result, you'd probably get quasi-polynomial time instead of polynomial time. Although kind of intriguingly, that's not really the reason why in our proof we get quasi-polynomial time, but yeah, that's what people had suspected beforehand. Yeah,
Thanks.
good question. All right, cool. Oh, and the other takeaway that I'm going to talk about in the application is kind of an example of different looking lower bounds. Great. And the other thing, hardness result we prove is about like a partial function version of MCSP. So this is like a very natural extension of MCSP, where instead of taking a truth table that's defined on all of its values, now, you're allowed to, the truth table could have like kind of star values in it where you don't care whether a function outputs yes or no. And one thing that I want to emphasize about this is that we're not taking like a more succinct approach where like maybe you could like define this truth table in terms of input output pairs, and that could be like exponentially more succinct. Maybe if the function is not defined on too many points. That's not what we're doing. We're still requiring that you have a truth table of length 2 to the n. It's just now it could have some stars in it. Yeah. So that's the input, and now the output is kind of very natural. Like, does there exist a circuit, usual type of circuit, and or not circuit fan in 2, with at most S wires that computes this function on all 0, 1 valued inputs. And historically, this like partial function version of MCSP has been kind of an important intermediate problem. So for that DNF MCSP hardness result, the way that it's proved is by first showing the partial function version is hard, and then reducing the partial function version to the total function version. So kind of historically, this partial function version has been an important intermediate problem. And so what we're able to show is that this problem is not in P under ETH. And if you're interested, like how not in P it is, it's like n to the log n. Like we show that it can't be solved in like n to the log n times. So it's like just barely outside polynomial time regime. And so I'm not going to talk so much about how this is proved, because I kind of want to talk about how the other result is proved a little bit more. But I'll mention some like nuggets related to like what's important for the proof. So like one of the key ideas here is actually like a very simple idea. It's that if you look at the OR function, the very simple function that just outputs the OR of whatever bits you put into it, that function we know has a ton of optimal circuits. And particularly because OR is kind of commutative, you can kind of take these ORs in any order you want. So it actually has like roughly n factorial circuits where like n factorial is coming up from like what permutation you choose to compute your OR in. And there's actually like a few more of them, but it's mostly coming from permutations. And so if you like squint at that, maybe the fact that computing the OR function forces you to choose some permutation could be related to like permutation problems. And that's kind of what we do. We show that there's this reduction from kind of like, this is like a crazy sounding problem, 2n by 2n bipartite permutation independent set. But it's not that bad. It has a big name, but it's not that bad. And we show that there's a reduction from this problem to partial function MCSP. And this problem was already known to be ATH hard from this work by LMS. And so that's kind of how this result is proved. And to me, what I really like about this result is it's a proof of concept that ETH is useful, and it's a proof of concept that gets really close to MCSP itself, at least in my view. Okay, so that's any questions on this slide? Great. So let me just recap a little bit about what the takeaways are. I think we have like a good example of how to use randomness in showing hardness for MCSP. We have a good example of using ETH to show hardness for MCSP. I didn't talk about this so much because that's going to be the subject of the rest of the talk. And hopefully you'll agree with me that these problems, morally should give us an indication about the hardness of MCSP. I think especially the partial function version of MCSP. And to me, the outstanding open question is MCSP not in P under ETH? And I really think that this should be provable with things that are like not too far beyond gate elimination. And, I haven't been able to do it yet, but I think it should be possible. And I don't think it's going to require like crazy new ideas, maybe like one new idea or something like that. So this is the end of kind of like the results portion of the talk. Next, I'll talk about this application and the ideas used in there. But if there are any other questions, I can be happy to take them now. Okay, great. So now I'll talk about our application. And so if you've tuned out by this point, or if I bored you or something, and like maybe you can, this part's not going to assume any background from the previous parts of the talk. So you can come back now. And it's going to be about large gaps in formula complexity between depths. So let me just review the model of constant depth formulas. So in constant depth formulas, the model is you have this like rooted tree of constant depth, and the nodes of your tree are labeled by and OR gates of unbounded fan-in, and your NOT gates are kind of at the bottom. And for us, the size measure that we're going to use, just to introduce some notation, I'm going to say L sub d of f is the minimum, f is some function, Boolean function, is the minimum number of leaves in a depth d formula, computing f. So this is just some notation. L stands for leaves, d stands for depth. Okay. And so the question I'm going to ask is, what is the power of extra depth? And in particular, I'm concerned with this additively. So how large can this quantity, LD of f minus LD plus 1 of f, be? And this is a very natural question. It's kind of asking like, what is the power of serial versus parallel computation in some sense, like where you're like, if you give me like an extra time step, how much more can I do? And I'm in particular interested in it like additively. Okay, so this is a natural question. What would you, if I asked you to study this, probably the first thing that you would do is you would say, oh, and just to remind you, this quantity means the size of the smallest formula of depth d. First thing that you'd probably do is like look at depth 2 versus depth 3. And there, it's very easy to prove that there's a huge separation. So if you look at the parity function, that basically has like 2 to the n size, it requires 2 to the n size DNFs. But at depth 3, you can do kind of exponentially better. And in fact, there are even better examples than parity that you could put here. So you get a huge gap between depth 2 and depth 3. What about at higher depths? So at higher depths, we actually know the following result from Hastad, who proves actually something much stronger than like an additive separation. So Hastad proved that there exist functions whose depth d plus 1 complexity is linear and whose depth d complexity is kind of exponential, and exponential in the way of the form 2 to the n to the omega 1 over d. So that's pretty cool. You might wonder like, okay, can we hope to do better? And you probably expect that the answer is no, because we don't really know any constant depth formula lower bounds that like go beyond this regime. And random functions, it's not clear how to use random functions in this either. In particular, if you pick a random f, this quantity you actually probably expect to be small, because like if you pick a random function, then morally the best circuit for that is like a lookup table. And for a lookup table, you shouldn't be able to, like depth shouldn't really buy you anything. So it's not even clear how to do better than this existentially. And so what we prove is an existential result that like kind of improves exponentially here. We're actually able to show that there exists some function, and this function is going to kind of be like a mix between a random function and parity, such that its depth d and d plus 1 complexity is greater than or equal to 2 to the omega sub d of n. So this means that there exists some constant depending on d. Roughly, the dependence is going to be like 2 to the n divided by 2 to the d or something like that. But there's some constant depending on d, such that you get a lower bound better than 2 to that constant times n. And just to mention some caveats, like our proof is like a really existential proof. I don't know how to make this explicit at all. And I only know how to prove it for formulas. I mean, I think it should be true for circuits too, but the way that it's proved is really kind of crucially using formulas. And if you tried to transform these formulas into circuits, like things would blow up and it wouldn't work. Okay, so I'm going to tell you a little bit next about how this is proved. But is there any questions about the statement of the result or the background? Okay, cool. So let me just say a little bit more about why I think this is interesting. I've just restated the theorem here. I haven't said anything new. One is that I think the fact that you could get something with this good parameters is kind of surprising, because like we don't know how to prove lower bounds in this regime usually. But kind of the more interesting thing to me about this lower bound is kind of coming back to this thing I mentioned earlier about like different flavors of existing lower bounds. In particular, the way that we proved this ended up coming out of our proof that depth D formula MCSP was hard. And the lower bound that came out of that was kind of very different than existing lower bounds, because like for one, it kind of works in a top-down way. And until now, we only really knew how to, or not until now, it's kind of been an interesting question whether you can prove top-down lower bound technique, top-down style lower bounds for constant depth formulas. The proof doesn't really use the switching lemma at all. And there's some kind of intriguing sense where this lower bound technique doesn't really fit into this like kind of huge barrier against proving circuit lower bounds related to the natural proofs framework. So I think that's kind of what makes it interesting. If you're interested in, how exactly this doesn't fit into the natural proofs framework, I have kind of a bonus slide on that, so you can ask about it. But yeah, that's why I think this result is kind of interesting. Okay, so now let me tell you about how it's proved. So the proof strategy is as follows. It's like a very natural proof strategy. I've just restated the theorem here. In the D equals 2 case, I'm just going to use the parity function. And in larger cases, what I'm going to do is I'm going to come up with a way to lift a separation to higher depths. So if you give me a function such that this quantity is large, its depth D has a large D versus D plus 1 gap, I'm going to come up with a new function H that has a large D plus 1 versus D plus 2 gap. And what I'm going to pay is I'm going to pay some constant in the exponent. So each time I increase the depth, I'll kind of lose something there. So that's kind of the high level idea. I think it's a very natural idea. But the question is like, how would you come up with H? And kind of as like a fun exercise, maybe I'll like pause for a few seconds. So like maybe you might want to guess what you think H might be. Yeah, like if you had some function that had some separation of D versus D plus 1, what kind of function H would you guess has like a large D plus 1 versus D plus 2 separation?
Parity of a bunch of independent Fs.
Yeah, that's a good guess. And I think it's a guess that people haven't been able to really make work, which is kind of surprising because actually, I guess there may be two ideas that people come up with naturally. That's one. Another thing is like maybe you could come up with some function where we replace its inputs with parities, and and people haven't really been able to successfully analyze that. But I think it would be interesting to study that and see like does it actually fail, or are we just not able to analyze that? But yeah, okay, good guess. So here's how that function will be defined. So let me just repeat what we're trying to do. Our goal is to lift gaps to larger depths. And we start with a function f that has a large D versus D plus 1 gap. And our goal is to come up with a new function h such that it has a large D plus 1 versus D plus 2 gap. And for this slide, because it's going to make things a little bit simpler, I'm going to make the following simplifying assumption. Assume that every formula that we're going to consider always has to have an OR gate on top. It turns out, this isn't too bad of an assumption to make, and you can do some De Morgan formula tricks. Not De Morgan's formula, De Morgan law tricks to get rid of this assumption. But I don't want to get into it now. So let's just assume that all the formulas have an OR gate on top. Okay, so here's what you're going to do. I'm just going to pick a new function g uniformly at random, and g is going to be on many more inputs than f is. So you should think of g as some really hard function relative to f. We're just going to pick some random g, and what we're going to set h to is we're going to set it equal to f on the inputs x anded with g on the inputs y. And x and y here are disjoint. So this is kind of like a direct sum between f and g. And morally, the intuition here is that in order to compute h, kind of naturally you want to do it with an AND gate on top. But I restricted to the case where there's an OR gate on top. And as a result, maybe this like top level of OR gate is not going to be so useful to you. So you're going to kind of lose a layer of depth there. So that's like roughly some intuition, but let me tell you what the formal theorem statement is. So in order to make the formal theorem statement, I'm going to just introduce some more notation, which is L OR sub d plus 1 of f is going to be the minimum number of leaves in an OR top depth d plus 1 formula for f. And so the formal theorem we prove is that with high probability over your choice of g, you actually get that the d plus 1 complexity of h, okay, so I should say, so in this theorem statement, there's going to be like lots of like little ands and ors on top. For now, I would suggest you just ignore them, and maybe like after we go through it a little bit, take them more into account. So we show that like the d plus 1 complexity of h is actually lower bounded by the d plus 1 complexity of g plus the depth d complexity of f. So the easy lower bound to prove here is it's not too hard to prove that this quantity is lower bounded by the d plus 1 complexity of f plus the d plus 1 complexity of g. But what's cool here is that if you choose g at random, actually you can improve this quantity from d plus 1 to d. And it turns out, like, so there's also like a pretty easy upper bound you can get. I won't tell you how to get the upper bound, but it's not too hard. Where you can upper bound this by like the depth d complexity of f plus the depth d complexity of g. And so what that means is, you know, if you look at the left-hand side here and the right-hand side, they're almost the same. Like, so these first two terms are the same. But these two terms, basically, one is the depth d plus 1 complexity of g, and one is the depth d complexity of g. Turns out if you choose g at random, these two quantities can be made really close to each other, like kind of multiplicatively arbitrary close to each other. So actually this lower bound here can be pretty tight. Yeah, so that's kind of our main lower bound theorem. And if you want to prove this gap separation theorem, it turns out you won't want to choose g completely at random. You want to choose g such that like this upper bound and lower bound are tight. But yeah, that's the idea. Are there any questions? This is my like second to last slide, by the way.
So this is really, sorry, somebody else want to, yeah. This is giving me just very random high level memories of kind of sum check protocol for IP equals P space. And I'm wondering if there are connections here. So that's one possible direction. I'm just curious about if that's come up in this. Because you're sort of randomizing something and then sort of essentially reducing a degree in one step. Mm-hmm. So I'm not sure if that's a line of reasoning that even applies here, or if it's an analogy that works.
So, yeah, that's an interesting question. I'm not sure. At least how I know how to prove this, I don't quite see an analogy with sum check, but maybe there is some analogy you could make. I think that's an interesting question. Yeah.
And then maybe a follow-on question too is, you haven't talked about relativization here at all. Or is there any notion of relativization in any of the stuff you're talking about?
Yeah, that's another good question. I'm not sure if you can really, like, everything we do is very specific to kind of this underlying circuit model. Like this proof would definitely break if you had oracles in there. In particular, I don't even know how to prove it when you allow parity gates, like let alone arbitrary gates.
Okay.
So yeah, I would suspect that this doesn't relativize.
Okay. Thanks.
Can I ask my question now?
Yeah, sure.
So you also need a formula size upper bound for depth d+2, right? For h and therefore also g, but g is random, so it will require a very large formula. Is this in a subtle choice of sort of a not quite random function g that you ensure that it has a small formula of depth d+2?
Yeah, that's a great question. So what's going to happen is that we're going to have this random function g, and that's going to blow up the d+2 complexity a little bit. But kind of the nice thing is that you have to pay for g on the d+1 side and the d+2 side. So like that's where we actually are able to, like, whatever, if we choose g at random, you know, we know it's going to require large formulas, so we actually can put that into the d+1 lower bound and kind of recover that. So we kind of get it on both sides, so it doesn't matter too much. Did that answer your question? Or
Yeah, sufficiently. Thanks.
yeah, great. Yeah, so that oh yeah, maybe I'll just ignore that for now. So that's kind of the end of my talk. I'm happy to answer any questions. Some interesting open questions I think are like, can you prove MCSP is not in P under ETH? Can you prove an analogous result for circuits? Can you prove a better gap theorem? You know, is naturalization something that we actually avoided? And finally, like these connections to cryptography, I think are very interesting. Is MCSP hard if and only if one-way functions exist or something like that? All right, great.